So this graph is a graph. They don't tell you very much about it. They tell you it's a twice differentiable function. Okay, and this actually it's not significant for this problem, but twice differentiable means that the f of x is smooth and continuous. Okay, so f of x and the f prime of x is also smooth and continuous. Okay, so it means that they're both smooth and continuous. Okay, so the fact that it's twice differentiable, I'm not too sure it means a lot other than we need to have the differentiability for the second derivative. So it says on the interval -2 to 5, it has the second derivative is always positive. So that means it's always concave up. And it says that the derivative at 3 is equal to 2. So slope is equal to 2. Okay, so we have a graph. It's going to be from -2 to +5. Okay, and at x equals 3, we have a slope of 2. Okay, and it's also always concave up. So A says draw a possible sketch. So we know that it's going to be curving up the whole time. Okay, so let's say the slope of 2 is like that. And it's going to be curving up the whole time. Okay, so those are going to be my endpoints. And the slope of, right this point here, okay, we'll say that's the slope of 2 through that section. Okay, so there's our possible sketch of this. Could I have made this point higher? No, because this is a positive slope through here. So actually, sorry, could I put this point lower? No. Although we could have positive concavity like that. The fact that this positive slope through here makes that point higher and that point lower for now. But although this point, in terms of coordinates, it could have kept curving up much quicker like that. Okay. Okay, so it says determine if f prime 0 is less than 2, f prime 0 is greater than 2. Okay, if the slope is 2 here and positive concavity, what it means is the slope is getting more and more negative or less positive through that whole region going in this direction. And in going this direction, it's going to get more positive. That's what positive concavity means. As I go to the right, I get more and more positive slope. That means the reverse this way, more and more negative slope. Okay, so that's kind of our boundary. From this point on, the positive concavity means slope is increasing. Okay, so it's getting more positive. In this direction, from this point, this opposite must be happening. Slope is decreasing. We're getting more negative. Okay, so if that's the case, then is it possible for the slope this side at 0 to be less than 2? Well, yes, that's true. Okay, so that's okay. I get 0 slope here. Is this possible for that slope to be bigger than 2? Well, if it's getting more negative and decreasing here, it starts off at 2 and it can't ever get bigger than 2. In fact, might get bigger negative, okay, because it might turn up like that, but it can't get bigger than 2. So that is not correct. So we're going to have to get rid of that. Okay, this is not possible. Okay, and because of this issue here that's always decreasing. So what about the slope at 0 being greater than the slope at 4? Okay, so slope of 4, well, the slope of 4 is going to be bigger than 2. The slope at 0 has to be less than 2. So no, that's never possible that the slope at 0 could be greater than 4. The slope at x equals 4. So that's not true. Okay, so we have that as the only possibility. Now, this could be really steep like that, and it could mean that the derivative, the absolute value slope, could be greater than 4. That's possible. Okay, that would be a situation where the graph may have looked like this, right? Okay, so actually that's not at 0, but at like negative 1 or something like that. But given that there's the actual slope value, this slope could be a big negative value, but it can't be bigger than whatever value we have here. That's impossible. Okay, so this problem here is an optimization problem again. So to do these optimization problems, we again need to make sure we know the quantity I'm optimizing. So in this case, we're minimizing the amount of material needed to make a pop can. Well, pop can is made from a cylinder, and it's going to have a net that looks like this. Okay, and to make the popcorn, the material needed is going to be surface area. Okay, so I need to come up with an equation for surface area. So surface area for this net is going to be 2 circles, so pi r squared, and we need 2 of those, plus the circumference of that circle is going to give me the width of that rectangle, and we have height, so we need to use that rectangle, which is going to be 2 pi r. That's the width times the height. That'll give me the 3 surfaces, 2 circles plus the 1 rectangle. So there's the equation I'm going to minimize. Now, if I could differentiate this in terms of one variable, then I could solve this problem, but I've got too many variables here. So I need another relationship. So I need to look for another relationship in the problem. So the material needed surface area, and then I have volume. I've been given volume for this problem. The volume then represents a second relationship. Okay, so volume is 355, and that's going to be found by the area of the circle times the height. Okay, so there's the formula for volume of a cylinder, pi r squared times height. Now, I can eliminate one of the variables using that other relationship. Now, it's probably easiest to get rid of the h, instead of trying to solve for r here and r squared to replace there. So I'm going to solve for h. So h is equal to 355 divided by pi r squared. Okay, so that I'm going to then get rid of the h in this expression here, and then I will have a surface area function as a function of r. Okay, that's my variable r. So I get 2 pi r squared plus 2 pi r, and instead of h, I'm going to use an equivalent r expression for h. So 355 over pi r squared. Okay, and you can see that there's going to be parts that simplify here. The pi's are going to cancel out, the r's are going to cancel out. So now I have my surface area equation, surface area as a function of r, the radius of the circle, is going to be equal to 2 pi r squared plus 2 times 355 is 710 over r. So this is a function I can now differentiate to find the min or max of. So I'm going to differentiate and find where it's equal to 0. So my derivative is 4 pi r plus negative 710 over r squared. Make that equal to 0 and solve this equation. I'm going to move the negative 710 to the other side. So I end up with 4 pi r cubed is equal to 710. Solve for r. I get 710 divided by 4 pi, and the radius will give me the least amount of surface is going to be the cube root of 710 over 4 pi. Okay, so I don't know if that answers the question yet. So it says determine the minimum amount of material needed. So I actually have to calculate the surface area. So I'm going to take that answer. I'm just going to plug that back into my surface area equation and to actually answer the question. The surface area, the minimum surface area needed, or the minimum amount of material needed, is going to be 2 pi times the cube root 710 over 4 pi squared, so 2 pi r squared, plus 710 divided by r. So I'm going to write this as a reciprocal of that. So it's going to be the cube root of 4 pi over 710. Okay, so it's going to be, maybe let's just clean that up a bit, make that look a little bit nicer. 710 times the cube root of 4 pi over 710. Okay, since I'm dividing by r, I'm going to, where is it, divide by r here. So I'm going to just flip that fraction over. Okay, so there's my solution. The minimum amount of surface area needed is going to be this surface area here.